Hey everyone. First off, let me thank the organizers and for inviting me to come here. I'm really happy to be here. You'll have to excuse me, I might be a little bit slow today because I flew from Berlin on Sunday, so I'm still dealing with the time difference and stuff, but I hope this will help wake me up and hope wake everyone else up too. The title of my talk is Collective Behavior from Surprise Minimization. This is going to be a summary of work from my PhD. And the idea is kind of to take all these collective motion models that we've been hearing about over the last days and put a kind of Bayesian gloss or a Bayesian interpretation on it. So it's very in line with the sort of themes that people like Ahmed and Ian and others were talking about yesterday, bringing a cognitive lens to studying collective behavior and kind of making our models more expressive and more biologically realistic. Let me just get this little GIF going. And just a little background on me. So I'm currently a machine learning research engineer at Verses, but I did my PhD in Constance with Ian, and I was co-advised by Carl Friston at UCL. And that's where kind of this idea of surprise minimization comes from his influence. So just a quick overview of the talk. So I want to give, before we dive into the actual collective motion modeling, I want to give some background on Bayesian cognitive science, this kind of Bayesian turn in the brain sciences that's happened over the last 20, 30 years, and then also active inference, which is the core process theory that inspired the title of surprise minimization. So we'll get into the Bayesian inference and the Bayesian brain revolution, as people call it. And then once that background is established, because I think it's important that we all are kind of on the same page about the Bayesian brain, then we can apply the concepts that we overviewed in the first part to the problem or the interesting phenomenon of collective motion, with an eye to things like schooling fish, flocking birds, herding ungulates, all the kind of things that we've heard about and seen real examples of yesterday. And each of these things will have little subpoints, but it's not important that we go into those. So the Bayesian turn in the cognitive sciences. This actually has a much longer history than the last 20 years, but in the last 20 years, I would say people started appreciating and kind of really thinking of the brain as fundamentally in the game of inference. So the brain is not some kind of feed-forward feature detector that takes sensory inputs and outputs actions, but rather the brain is really in the game of inferring the hidden causes of sensation. So you're faced with a sensory array of data, and what the brain is always trying to do is trying to guess what is the best explanation for the data. So the reason I mentioned the historical legacy of this is it was first, actually there's even older history, but the kind of in the Western canon, it's recognized that Hermann von Helmholtz first came up with this idea of perception as unconscious inference. So even the kind of rawest low-level sensory perception is actually already some form of an interpretation or inference. So let's just get into a very concrete example. Visual illusions are a great way to illustrate this. This is called the Necker cube. It's a 2D ambiguous visual stimulus in the sense that you see this and some of you may be seeing the front face of the cube as here, and others of you may be seeing the front face of the cube as there. And I can kind of trigger you to see one or the other by highlighting them. And this is also an interesting kind of bistable phenomenon where your perception of the facedness or the depth of the cube may actually oscillate over time. Could probably relate that to bifurcation theory if it hasn't been done already. So the idea is your phenomenological perception of what side of the cube is the front is basically implemented as some form of posterior inference. So what I'm showing here is basically a posterior probability of is the front of the cube here given this impoverished, or I can use the clicker, given this impoverished 2D data, or is a better explanation that the front of the cube is there given this impoverished data. So even by these very early levels of visual perception, you're already doing some kind of model comparison or some kind of evidence accumulation, and you're trying to say, okay, what is the best explanation for the sensory data? I actually was meaning to email Ian to get his little video of the 2D stimulus that we see as 3D. That's another great example of perception as unconscious inference. Depth inference is also really a good example of this because the stimulus is underdetermined with respect to the explanation of that data. This is another great one where you probably are seeing a white boundary but that white boundary that you're seeing or perceiving is actually the result of some kind of inference, right? It's not that white boundary that's sketching out a triangle actually exists, but we're kind of putting that, it's an interpretation. So perception is already at the very early levels a synthetic inferential process, interpretive process. And this is kind of the idea that will undergird the rest of the themes in this presentation. So this idea of perception as unconscious inference, I don't think Hermann von Helmholtz put that in such like formal Bayesian terms, but later in the 20th century, this was formalized. Well, Thomas Bayes himself, of course, came up with Bayes' rule, but we started thinking of the brain as perhaps doing something at least proportional to Bayes' rule, where we're combining evidence shown in red, so like sensory evidence, the raw data, with some prior expectations about the causes of data. That would be like the blue distribution and this P of A up here. And it's the combination, or literally the product of those two things, that forms our perception, which is our posterior belief, this green distribution. And one of the like classic kind of things about Bayesian inference is that you can nudge your posterior expectations or your explanations of the data by manipulating the relative precision or the reliability of these signals. So if you trust the sensory evidence more, your posterior distribution, this is a very like one-dimensional Gaussian case, will be shifted in the direction of the evidence. Another way to do that is you can actually decrease the prior precision. And of course, this is all symmetrical. You can manipulate precisions or variances of distributions in whatever way you want, and your posterior will be accordingly dragged between those two sources of information. So this is often referred to as like a kind of Bayesian revolution because it really took classical models of cognition and perception as kind of feed-forward cascades of feature detectors, which we have to admit have been very successful in the context of, say, convolutional neural networks, which are really formulated in this kind of feed-forward. Early layers do, edge detection, later layers do object detection or something. But the Bayesian framework has taken this idea of feed-forward perception and kind of done a strange inversion, where instead we think of computer vision as more like inverse computer graphics, where instead of saying, is this a picture of a Toyota or a Tesla, I'm saying, what is the most likely explanation, the latent causes that explain the raw pixel data that I'm seeing? So here, instead of doing feed-forward feature detection, what you're doing is inversion of a generative model of your data. You posit some model of how is my data generated, and then given the data, I say, okay, what are the most likely explanations or the most likely latent states, like this top row of blue nodes, that best explain yeah, please.
Maybe just a footnote to this. So recurrent neural networks and ANNs have been a dominant sort of paradigm. And analyzing the latent states and the hidden states there has been sort of, and then seeing what emerges, whether it's modularity, et cetera. Mm-hmm. So it's not just this binary of feed-forward and Bayesian. All of that.
Oh, yeah, sure. Yeah, that's a good point. So, right, there's also non-Bayesian methods that are not feed-forward, is basically your point.
And also are about latent state discovery and inference.
Yeah, and about latents, yeah, for sure. But as soon as you incur inference, or in my opinion, as soon as you incur like a latent state, you are kind of implicitly, whether you're writing it down explicitly or not, you're doing some kind of inversion of a generative model. Actually, I would even, so this is like the radical Bayes glaze, but even feed-forward feature detection, I would argue is just some kind of amortized inference or some kind of inversion of a generative model. But when I'm writing down my sequence of conv layers, I don't actually have to write down the generative model. But doing a forward pass is a kind of inference, but we're just not being explicit about it. And the whole Bayesian thing is just, let's be explicit about it. Let's write down the mapping from hidden states to observations with explicit distributions, let's say, like likelihood functions. So I think, but it is a good point that there's like loads of stuff about hidden state estimation that's kind of not fully embracing Bayesian terminology, but I think it's always implicitly there, as long as you have something that's not determined fully by the data. Okay, so so that's just like Bayesian theory in general. So one of the things that underlies this talk is a particular process theory for how you can do Bayesian inference that's called predictive coding or predictive processing. So the idea is, okay, I want to get this posterior distribution over the hidden states of the world that generate my data, represented here. This is my posterior belief. And let's say I represent it with some, it's like has one moment, it's just fully determined by the mean of the distribution, mu. There's an efficient algorithm for getting that mu, that best mu that explains your data, and it's basically called prediction error minimization, where I say, find me the mu that minimizes this quantity called prediction error, where I'm leaving out some terms here, but effectively prediction error is some squared difference between the data and the current value of my estimate. So like there's no priors here, so this is actually just maximum likelihood estimation where my belief will just zoom to the data if I minimize this. But that's the idea. And the reason that this is compelling is because it's very easy for neurons to do this. That's why it's like considered biologically plausible. Predictive coding is a local, biologically plausible, quote unquote, algorithm for doing Bayesian inference on at least distributions that are characterized by like a few moments, like a mean and a variance. So more formally, we use a gradient descent on free energy to update the posterior means. So free energy in the context I'm using here, it's a more general objective that you can use to do a type of Bayesian inference called variational inference. But in the context I'm using here, you can think of free energy as just proportional to a sum of prediction errors. So a precision weighted sum of prediction errors. So minimizing free energy is the act of making my current estimate be as close to the true posterior belief as possible. Basically, make mu as good an explanation of data as possible. So yeah, we can write it down as like a gradient descent on free energy. You don't have to always do a gradient descent. It depends on your distributions. But the predictive coding theory of the brain is basically saying that neurons, that maybe their firing rates encode something like the mean, their activity is doing some kind of gradient descent on free energy, where, as I said, free energy is like a sum of prediction errors, which in this case map very nicely onto the likelihood and prior information from the previous slide, where the red is like sensory prediction errors, the blue is prior prediction errors. So if you minimize this quadratic cost, then your mu is obviously going to be some kind of average of sensory information and prior information. So yeah, as I said, free energy is going to be this, in the context we're using today, it's going to be this quadratic cost function that's a sum of prediction errors, and free energy is an upper bound on surprise. So this is what, basically, if you see me say free energy, just think of surprise, hence surprise minimization, or a sum of squared precision-weighted prediction errors. Because I know there's a lot of people here who are probably very comfortable with minimizing quadratic cost functions. So if that's the framework you want to think about this in, that's totally fine. But it also has a connection to variational inference or like approximate Bayesian inference in the form of the free energy and thereby the surprise. So you can kind of map those prediction errors onto the distributions we looked at earlier. Very important, this will come in later when we talk about collective behavior and the interpretation of things like social forces, is there's always precision weights on those prediction errors. And these precisions are exactly the inverse of the variances of these distributions. So if I believe in my sensory evidence more, it means I believe this red distribution is tighter, my sensory data is more reliable, and therefore it means when I'm doing free energy minimization, I pay more attention to sensory prediction errors. And then the same logic obviously goes for the prior information. Yeah, please.
So when you say prediction, is there some sort of ground truth that you would compare the prediction to?
No, so the nice thing about the prediction error is it's just defined with respect to your current estimate, which is just, maybe the firing rate of a neuron and the data you're getting. You don't have access to the ground truth. That's why we have to do inference. So all you do is I try to make my estimator as close to the data as possible, subject to some prior constraints, which is this other thing. And the prior is also something that is, maybe encoded in the resting membrane potential. I mean, I don't want to read too much into like neurophysiology, but so the point is you never have access to the thing out there. You're just doing this process with data and then the parameters of your model, which will be like the priors and stuff and the precisions. Okay, so I just want to make this very concrete in terms of like a Bayesian filtering example. So before I start the animation, what I'm going to do here is on the top plot, I'll show you the sensory precision over time. At some point, I'm going to decrease the sensory precision, which means the variance of the noise innovations or the noise fluctuations will suddenly increase. And then on the bottom, I'll show you a kind of Bayesian filtering example where the green will show you the posterior estimate, which is estimated using this predictive coding prediction error minimization. The red will be the observations, which like halfway through will suddenly increase in noisiness. And then blue will be the prior, which will be some fixed prior assumption that the agent or the animal has about the source of its data. So you see that the green is kind of some Bayesian average between the sensory evidence and the prior in blue. You see like it trusts the data, so it was kind of, the green was approximating the red. But then I decrease the precision. So the noise increases, and we assume the agent knows that somehow. So it incorporates that change in precision into its model, into its inference, and then the green correspondingly gets dragged more towards the prior. So I think it's a nice way to kind of show that the prior and likelihood are kind of competing for where the posterior goes. Let me just take a sip here. Okay, so what about action? So I mentioned something called active inference earlier. So far, this has just been about passive inference. So active inference is the idea that, okay, so this is passive inference, right? The world, our estimate of the world is the result of doing some kind of free energy or prediction error minimization. And then we also have this ability to intervene or to feed back into the world through actions. And how does this fit into the picture? So if I'm just doing like Bayesian belief updates to get mu, and then I just have some extra cost function or like say planning algorithm that tells me the actions, that's just standard reinforcement learning. Maybe it's Bayesian reinforcement learning because I'm technically doing some inference first. So then the question is, okay, this is just belief-guided action. How is that different than standard reinforcement learning? Well, active inference actually gets really kind of deflationary about action per se, in the sense that in the same way as optimizing your beliefs about the world is a process of minimizing prediction error, you can do the exact same thing with actions. If you represent actions in your model, you can just say, choose the action that minimizes prediction error as well. So this is the idea of like both perception and action are kind of collaborating or conspiring to minimize surprise. And so what you do here is now we're saying, find me the action that minimizes, again, precision-weighted prediction errors, except now you see my data y here is a function of action. It could also be a function of hidden states indirectly if action goes through hidden states and then, but you represent that dependency explicitly in your model, which is basically the agent's assumption that as I act, I know I have some representation of how my actions change my data. So that when you're doing the minimization of this, like quadratic cost function, you're taking into account the fact that your actions have consequences. And so under active inference, in summary, everything is about minimizing prediction error, aka surprise. So there's two ways to become less surprised: change your beliefs, which is perception, what we just talked about, or change the world via action. So you're minimizing prediction error by changing your actions. So again, coming back to this kind of classical sandwich model of cognition where you have perception, feeding forward to cognition, feeding forward to action, we can kind of take this and what active inference does is it takes this unidirectional information flow with distinct phases of processing, and it says these are actually just two sides of one coin, which is there's always predictions flowing from top down to explain data, and there's basically two ways you can minimize the resulting prediction errors that happen when the prediction is compared with the data. So basically, data minus prediction equals prediction error, and that gets sent back up. So there's perceptual predictions, like what am I looking at? Am I looking at a Necker cube with the front over here or the front over there? And then the idea about motor control and action is that there's also proprioceptive predictions. So there's predictions about the state of my motor plant in the future. And that also incurs prediction errors. So like simple reflex arcs and kind of the firing of certain spinal afferents, for instance, could be interpreted as some kind of prediction error minimization. That's the idea, the kind of radical form of active inference where everything is, there's really no difference between perception and action. They're just two different sorts of prediction errors that you're minimizing. And there's been some work saying that there's evidence for this. If you just look at the architecture of like the descending like motor cortex to spinal cord and whatnot, it's a mixed bag in terms of whether that's true, but I think just the idea itself, maybe there's some isomorph to that in the world. Yeah, please.
I just have a question about kind of what setting I should think about this in, because as a human, I take a lot of actions every day, and some of them one could argue are meant to control my externalities in a way that they become, like I can anticipate better what's going to happen. Like I have a cup of coffee next to me, I'm going to move it to the center of the table so that there's a lower chance of it being over or something like that. But then there's many decisions that I would take that are curiosity driven. For example, as a researcher deciding what I want to study, if I would only come up with research projects where I already know what's going to be the end product. Well, there might be people who might be in favor of doing that, but generally you would want to kind of have some actions or to make some decisions that lead to potentially surprising outcomes. Because if they're not, like if they're 0% surprising, right, then they're not really informative.
Yeah, absolutely.
So what is active inference? What is kind of the setting and the scope of the setting that I should think of?
So this kind of like reflexive active inference, where you're just minimizing property set of prediction errors, I think it's better suited for things like shallow motor control. Like you can add some temporal depth into this if you kind of roll it out into the future, but it's better suited for the case of like what you described with the coffee cup. These curiosity-driven explicit planning actions, there's a different like setting of active inference that doesn't use this formulation, but it uses more explicit planning algorithms, where it's also a free energy functional, but you're kind of taking the expectation of that free energy into the future. And the weird result that falls out is if you minimize the expected time average of surprise, the best way to do that is actually to take actions that locally look like you're getting more surprising data. So this is where the concepts of like information gain or Bayesian optimal experimental design come from. You can think of curiosity-driven actions as actually things that you surprise yourself with in the short term to ultimately actually get a better model, which will minimize free energy even more. But this sort of proprioceptive stuff, to my knowledge, has not been used to adequately explain like curiosity-driven, like that sort of investigatory action, information seeking. Yeah. Yeah. Yeah, absolutely. Yeah, you can think of it as exactly like prediction errors coming from your retina or from your cochlea or like something.
Or is it sensory?
I use it interchangeably with sensory, but I think that that's probably wrong. It probably is maybe more general than sensory, but I think of it as like sensory. Yeah. Good point. Yeah. I don't know where that falls. That's like there's a whole theory of like emotion as inference as well. I don't know which of those that is, or it's just a third category. But yeah, it's worth mentioning. Yep.
Maybe since we are on the different kinds of prediction error, the early appearance of it is in the 60s in control theory and in Rescola-Wagner in psychology that later on goes into the reinforcement learning in the 80s. And the free energy principle notion of prediction error, I think it appears early 2000s. So there was a whole precedence of other kinds of prediction errors in addition to these two, from value, from state prediction error, et cetera.
And there's also, there was predictive coding in image compression that it wasn't explicitly using prediction errors, but that's also from the 50s and 60s. Yeah, so it has actually quite a long history that predates the free energy principle. Yeah, predictive errors. Yeah, exactly. Yeah, and so anyway, there's just been a ton of applications of active inference to different, to explain different phenomena, usually in the context of single agents. That's why kind of my work is trying to extend it to multiple agents. Things like active sensing, whisking in rodents, that's a cool one. Recently embodied spatial decision-making, so you can show that active inference, not in the 3-target context, but for 2 targets, shows the exact sort of bifurcations that Ian was talking about yesterday. This is still a preprint, but this is really exciting because you can then relate the kind of bifurcation angle to a parameter of the generative model, so an actual belief about the statistics of the world. Anyway, there's a lot of cool stuff, so that's just a small smattering of interesting applications. Okay, so yeah, I'm already like 25 minutes in. So now we're actually going to get to the application. That was the build-up. Now we're in part 2. We're going to talk about collective motion. So I don't need to motivate this slide much, given all of the great talks we saw yesterday and today. So collective motion is clearly prevalent in nature. It's not just in like individual animals and like mobile social groups, but it's also in single animals, it's in humans, it's also an artificial and engineering phenomenon. Collective motion is everywhere. So people, it's obviously very interesting for me because it's like a classic example of a decentralized complex system where you get emergent properties from local interactions. Questions about universality. I mean, yeah, these are things I don't really need to tell this audience about, but there's a lot of interesting kind of like physics to collective motion and non-equilibrium physics to it. And then it's relevant for biologists for many reasons, evolutionary, ecological, and then cognitive and neurobiological. So I'm going to kind of first introduce the self-propelled particle models, the kind of physics models that we've discussed a lot yesterday in particular, and also this morning. So in the physics-based models, right, you just represent agents as self-propelled particles that have some velocity that moves them through space. And then the environmental forces that kind of summarize things like the positions of other neighbors, the positions and velocities of neighbors and targets, those things kind of have this ballistic Newtonian mechanical effect on the focal individual's velocity, where they're kind of just bombarded. There's some simple transformations here that kind of summarize the whole action perception loop. And they're nice because this kind of abstraction allows you to do analytics where you can take continuum limits, do hydrodynamics. It's really nice, and these models are beautiful for many reasons. The classical approach should be compared not just with cognitive approaches, but explicitly belief-based approaches, where instead of the environment just providing these kind of fixed forcings on the velocity vector of the focal individual, what we have instead is we have a data-generating process where the environment actually stochastically or deterministically, but from the perspective of the agent, probably stochastically, creates some data, some actual sensory impressions. And what the agent has to do is not take the environmental states per se, but take these sensory impressions of the environment and then do some kind of inference, do some kind of estimation of what are the best, what are my best probabilistic estimates for the states of the world given the data I'm actually receiving, and then based on those beliefs, do some action. So you're really taking these simple sensory motor functions and really unpacking them in terms of an active inference process. And that's kind of what distinguishes these belief-based approaches. So I think this is not this is very not my, I'm not the first one to say this. This is something that many people, Ian, others in the collective behavior field have been saying for a while. So this paper by Renaud Bastien and Pavel Romanchuk has a great sentence about this. By ignoring perception and the explicit processes cognitive processes that animals go through and rely on these kind of ad hoc rules, we're limiting our understanding of the underlying complexity of the problem. So there might be kind of new degrees of freedom that are discoverable just by the fact that we're explicitly modeling the perception action cycle. So we're taking, instead of going from raw sensory data to response, we're interpolating and putting this process of inference in between. So now I want to stop doing background and motivation and actually get into what this paper was about. So what we wanted to do is write down what sort of model of the world an agent in a mobile group would have. What kind of generative model might they posit that explains their sensory data? And then the idea is by doing Bayesian inference with respect to that model, what you get for free is collective motion and interesting collective dynamics. And it's not just a recapitulation or a rewriting exercise. We actually want to see if by doing this, do we reveal new things and can we get new behaviors that we weren't able to see before? So our first step is, okay, what is this generative model? What are our priors? This is a factor graph notation where the circles are random variables and these boxes are factors, or basically things that represent things like priors and conditional distributions or likelihoods. So we have to write down for an agent in a self-propelled particle agent, what are the priors it might have and what are the likelihoods it might have. So it's going to have some belief about some latent variable in the world that gives rise to its data. And equipped with this model, the agent, by doing inference, will then give rise naturally to social forces, milling, schooling, stuff like that. So the generative model we write down basically captures the agent's inbuilt assumptions about, let's say in the case of seeing a shadow of a dog and inferring that it's a dog, there's actually a dog around the corner. The generative model you use to come to that inference that, oh, there must be a dog around the corner, that generative model will capture assumptions about things like optics, light refraction, are there dogs, are there cats, things like that. So these are the sorts of assumptions we're going to write down for a self-propelled particle in a mobile group. So the way we do this, and this is not a unique solution, by the way. Like there's many different general models you could write down, but we were explicitly interested in kind of writing down the model that would recover things like the V-check model, the cousin model, these other kind of classical models, because then once we have the equivalence, we can start understanding things more generically. So what we posit is that agents basically represent the distance between them and their neighbors. So it's a very coarse-grained, like one-dimensional variable. Here, we're actually partitioning it into several distance variables, but for the purpose of explanation, you could think of they're just representing some coarse-grained average distance between me and my neighbors within some interaction radius. That's the latent variable that's out there in the world to which they don't have access. And what they imagine is that that latent distance variable is stochastically giving rise to observations. So maybe through some Gaussian distribution, right? They're actually seeing little noisy examples of the distance, but they never see the distance itself. And if we assume that their belief about that data generating process, it has like a Gaussian form. So they assume that the true distance is here, but what I see is some fluctuation around it. Then we can get this nice predictive coding, free energy minimization thing that follows from like kind of the exponential form of this distribution. Okay, so this is where the interesting part comes in about how do you get social forces? Because we could imagine if we just have this model and they're just doing, let's say, maximum likelihood estimation, there'll just be a bunch of particles maybe moving forward and then just estimating what the distance is between them and their neighbors, right? There's no goals, there's no desires. So then what we posit is we say, let's imagine that they have some prior about that distance. I believe that on average, the distance between me and you fluctuates around some fixed point. It doesn't have to be a fixed point. It could also be like a dynamical prior. That's like some time series model. But for now, we just assume that they believe that the hidden distance variable is at some value. Actually, this could just be recapitulated as like a single Gaussian prior, but technically what we have them do is we have them believe that the distance is xl here is relaxing exponentially to some fixed point of eta. So basically an OU process, a linear diffusion that relaxes with rate alpha to eta. But this whole SDE just has a stationary distribution that's proportional to this. So you could just think of them having a fixed prior about the distances at eta. So they just believe a priori. Whether that's right or not, they just have that belief. Okay, so now this is where the active inference bit comes in. If you then equip it with this weird biased model of the world where they believe the distance is at that value, and then you do these predictive coding rules. You just say, okay, how do I change actions to minimize free energy, and how do I change perceptions to minimize free energy? And we assume action is their heading vector, which is a standard assumption in these self-propelled particle models. What you get is basically a update equation for the velocity that's a product of two terms. One is this term, which is how do my observations, y, change as a function of my velocity? This is this kind of sensory motor assumption or this belief that the agent has about how does my velocity affect my perception? And then you have the second term, which is how does the free energy or the overall surprise change with respect to the observation? So this is just doing the chain rule on the gradient of the free energy with respect to velocity. So this first term you can call a reflex arc or sensory motor contingency. That's how they kind of call it in the active inference literature. And then this second term, which is the gradient of the free energy with respect to the observation, is exactly a precision-weighted prediction error. And so then what you get, if you actually have a realistic model of how their observation of the distance couples to their heading vector, so we assume the agents just know that because it's a very simple kind of linear geometric relationship, and then you write out that gradient in terms of like actual terms, what you get is basically a prediction error weighted vector. And this vector, which is exactly that sensory motor contingency gradient, is the classic social force vector from the cousin model, for instance. So this is like the vector that mediates attractive and repulsive forces. It's just a vector that points from me to the average position of my neighbors. But we don't bake this vector in at all. It just falls out by doing free energy minimization with respect to this biased model of the world. So this vector itself is then scaled by a precision-weighted prediction error. And what this precision-weighted prediction error does is it measures the difference between the actual sensed distance between me and the sense distance, which is just some stochastic observation, and my belief about that distance, which is also being optimized to minimize prediction error. So for free from this model, you get attraction and repulsion, where attraction is when this prediction error is positive, so the data I'm seeing is greater than my belief about the distance, and repulsion, which is when this prediction error is negative, so when the data I see is smaller than my expectation about the data. So we kind of get this almost like proportional integral derivative controller that has a nice probabilistic interpretation, because the strength of the repulsive or attractive force is determined by the precision, which is the beliefs about how noisy the data is, and then the sign, which determines attraction or repulsion, is determined by the sign of the prediction error. And this also relies on this belief about the distance being biased by the prior, right? So if I'm also doing inference, then my beliefs about the actual distance, my belief about x, will relax very quickly to this biased prior. So what this means effectively is that agents will kind of just move themselves in order to make sure that their observation of the distance is always at this fixed point. And that just comes from them having this kind of weird biased model of the world in which they think the distance is always at some weird value. So that's how you get like the average nearest neighbor distance from like a Bayesian framework. You just assume agents have a weird model of the world where they think everything converges to this fixed point. Oh, am I going backwards? Okay, yeah. So anyway, we take these zonal social force models and we kind of turn them, instead of having this discrete transition between attraction and repulsion based on like some threshold radius like you have in the cousin model or the V-check model, now we have this kind of smooth probabilistic control of action that's based on the actual prediction errors. How much is my data below my belief about the data? If it's very low, then I'm gonna swim away. And if the data is greater than my expectations, I'll zoom towards my neighbors. So that's how you get kind of smooth PID control like attraction repulsion out of active inference. And it all basically just follows because we have this nice quadratic cost function whose curvature is determined by that precision. Anyway, so if in the full model we used in the paper, we actually have multiple distances. So they don't just represent the distance in one overall zone, but we actually kind of split it up inspired by the fact that we have like different angles in the visual field. So they're doing distance estimation for this sector, this sector, this sector, this sector. And then what you get as a result, again, just applying the same math as before, is now you get a prediction error weighted sum of social force vectors going in the different directions. So what this means is that agents will effectively zoom or move more or less in one direction proportional to how surprised they are by the data in that direction. So if I'm getting very surprising data from the left, so suddenly my belief about the world is very wrong, then I'll actually correct left, either by zooming towards my neighbors or zooming away from them. So you kind of get this kind of for free attentional modulation of behavior just by the fact that we're using prediction errors rather than fixed behavioral rules. There's an important addendum about like how we're actually computing these observations. So technically, they're not just seeing the raw distance, but they're actually seeing the time derivative of the distance as well. So they're not seeing just the distance, but they're actually seeing what is called a generalized coordinate representation, where they're seeing the instantaneous time derivatives of the data. You can do like as many derivatives as you want, but we truncate it at 2. And then this is more of like an interesting trivia for, I would say, collective motion people, is if you assume that they see 2 temporal derivatives where they're observing not just the distance between them and their neighbors, but also like this derivative of the distance, which is kind of like a looming or receding stimulus, then the prediction errors are actually these prediction errors defined on the time derivatives of the data. And then what you recover from this is something that was posited by, I think, Pavel Romanchuk and Lutz Szymanski-Geyer back in, actually originally in 2009, but this is from 2012. And then Ian has worked on some papers with them in the context of locusts, which they call selective attraction and repulsion, which is this idea that locusts are not responding to just how far away their neighbors are, but how much there's a looming or receding stimulus. So we get this kind of looming-like stimulus from the fact that we assume agents are not just sensing the distance between them and their neighbors, but the time derivative. So it's not the same as the velocity vector, but it's the velocity of the distance. So it's an important distinction. So anyway, you can analytically relate this, this prediction error to effectively the selective attraction repulsion force from these older papers. So it's just a kind of nice unification that Pavel pointed out to me last time I ran into him. Anyway, is there evidence for use of prediction errors in the world or in animals? There's mixed bag, I would say, on humans, but there's a lot of overwhelming. I mean, overall, I think I buy the story that humans are doing some kind of predictive coding. But there's also some recent evidence that fish, or certain species of fish, are paying attention to body orientation changes, which is kind of proportional to like a looming sort of stimulus. So this is not the same as velocity, but it's the change in the perceived body orientation. There's some interesting work on measuring prediction errors in VR with zebrafish with 10 minutes school. And then there's also some interesting predictive stuff with the cerebellum also in zebrafish. And also I think this paper didn't get that interpretation at the time it was published, but also this interesting, more collective level predictive prediction error minimization, which is basically error correction, which you can always kind of interpret in some kind of predictive coding sense, which is with how army ants were building scaffolds and like bridges and stuff. Okay, so anyway, that's the framework, that's the generative model. I've shown you how attraction, repulsion, you get them for free. So then the idea is, okay, let's simulate these things, doing both perception by minimizing prediction error and doing action by minimizing prediction error. And what you get are, unsurprisingly, these nice collective regimes. We have milling, disorder, polarized motion. I'm speeding through things because of time, but you can basically show that the regime, the phase diagram of parameters under which you achieve the different regimes is a function of the no longer like behavioral weight parameters, but actually the agent's beliefs about the world. Right? Because now these weights have been interpreted in terms of precisions, like beliefs about how noisy the world is. And so now when we're constructing phase diagrams, we're constructing them in the space of beliefs, no longer in the space of these kind of weighting parameters. So this is just another one of the many benefits of taking a cognitive approach, where we think that the parameters we're positing maybe have some more biological realism, or they can maybe be tested experimentally, insofar as we believe that something like a prediction error or precision is being represented in the brain. I just want to like make a kind of conceptual point about the difference between kind of classical multi-body particle systems and these like free energy minimizing belief-based systems. So in potential systems, we usually define some energy function on the configurational states of the system. I know I'm going to do an equilibrium assumption here, so I know for non-equilibrium we've got extra weird terms in there, but you just assume that basically there's some global function of the configurational states of the system, and then you get collective dynamics by basically taking the partial derivatives of this energy function with respect to the different agents. And so if your state space is like the positions and momenta of all the particles, then you define some energy function on that space, and then you get collective motion or aggregation or whatever your phenomenon of interest is by doing some kind of gradient descent on this energy function. This again is equilibrium. If it's not equilibrium, we have all these extra things going on. Let's contrast that with the collective Bayesian active inference systems, where instead we have a local functional of probabilistic beliefs about one's environment. So the individual dynamics are driven by two gradient flows. There's one minimizing free energy with respect to action, and one with respect to my beliefs. So this is not a function of the states of the system, it's a function of the agent's observations and their beliefs about the states of the system. So the actual like kind of analytics of finding like the fixed points of a joint free energy minimizing system, I expect you can maybe like use an augmented state space and still formulate as a potential function of the states of the system. But I think there's going to be probably more clever ways of doing analysis on these systems that takes advantage of the fact that your energy function are private functionals defined on the space of probabilistic beliefs about data. They're not functionals defined on the physical configurations of the system. So you have like this agent has its own free energy functional. If it's Gaussian, that's some nice quadratic function. That's a function of its own observations and its beliefs about some latent variables. And so perception and action is achieved by doing gradient descent on this functional, not on a function of states. It's a functional because it's a function of beliefs, which themselves are a function. And then the same, there's a private free energy functional this agent uses, and that's a different energy function than in the global case, right? If we're doing global energy minimization, everyone is taking partials with respect to the same energy function. This is a very different game. everyone's free energy is kind of being contextualized by each other's actions and observations. Okay, so, and now I'm just going to get quickly into the results of the paper, because, yeah, we don't have much time. But so we did a bunch of questions. How do the properties of individual models relate to collective outcomes? So we reinterpreted classical force-based models in terms of, with quasi-uninterpretable parameters, now in terms of precision-weighted sources of sensory and prior information. Okay, 5 minutes. So yeah, so basically we're saying, okay, now instead of having ad hoc weight parameters, we have beliefs about the variance of sensory data. So maybe this is a more interpretable, biologically cognitive sort of parameter we can play with. And so now instead of movement being a sum of like social forces, it's a sum of precision-weighted prediction errors. And then we can kind of look at classic phenomena from the collective motion world and now say, okay, how does this phenomenon change or this effect change as a function of these cognitive parameters rather than these old school parameters? So we have a new form of model where agents don't just measure the distance between them and their neighbors, but between them and a distant target. And that's how we get kind of collective navigation or collective information transfer. This is based on old papers of Ian's from the early 2000s and there's loads of other work on this kind of target tracking stuff. So now what we have is a precision-weighted sum of two vectors, one which is like a social prediction error vector towards my neighbors, and another prediction error vector pointing towards the target. And then what we show is that even in the presence of a small number of informed individuals, basically individuals that have this new representation of a target distance in their generative model, we can get collective navigation, which is just basically recapitulating the old results. And we find that the kind of trade-off between the number of informed individuals you need to get a fixed level of accuracy, that value can be tuned by weighing the relative precisions, social precisions and target precision. So basically, how noisy do you believe data about the target is relative to data about social information? So you can trade those off and explore that space, and you find that there's kind of a sweet spot where you don't want to pay too much attention to either source of information to optimize collective accuracy. And then this is stuff that's actually not in the paper, but I was just curious. I did some experiments where you have two targets, and then you have agents kind of showing fission behavior. And what's interesting is that if you decrease the social precision, you actually get the nice consensus formation where they don't split into two groups. So actually they believe, they pay less attention to each other's observations, yet you still get this, and that's actually the case under which they get a consensus rather than fragmentation. And then we have these oscillation things, which I think Ian or maybe someone else showed evidence for in experimental systems. Maybe it was with Drosophila oscillating. So we see that as well in the system. Oh yeah, and then so the final, this is just a very final point. So, and this I think is the main kind of innovation of the paper, is you can imagine agents don't just do perception and action by minimizing prediction error, but they adapt the model itself online. So in all the previous experiments, the precision was fixed, their beliefs about the sensory noise, but now let's imagine that agents can actually adapt their beliefs about how noisy the environment is in real time. And if we know that that belief about the noise basically modulates the strength of the prediction error, then by adapting your beliefs about the noise, you're effectively changing the behavioral rules of the system in real time. Because usually the behavioral rules are fixed in these self-propelled particle models, but if you're doing inference about the rules, about the statistics of the world, then this is kind of a new class of collective motion models where previously fixed parameters are now also dynamic and adjusting over time. So we call this plasticity or learning. There's various things you can call it, where now you're actually changing your beliefs about the noise using the same principle, of course, just trying to get the best posterior belief over the noise value. And then what we show is that if you do a bunch of like perturbation experiments where you're kind of subjecting individual elements in the school to like phantom prediction errors, what we show is that only in schools that have this ability to do plasticity, you get very robust amplification of information. So this is a plot of showing, as a function of the time since the perturbation, what is the group turning response? So this is the total, like how much the group angle changes. And we find that relative to active inference schools that don't have this ability to do online behavioral plasticity, and compared to classic self-propelled particle models, like the cousin model in this case, that the learning-enabled schools have a much robust, more robust response. And this is like an example trajectory where the perturbation happened here, like basically a kind of like a little percolation experiment where you drop a grain of sand on one individual, so to speak. And then we also looked at things like the probability of the response as a function of the perturbation size, and then also the integrated turning angle as a function of the perturbation size. So we just like kind of try to understand the ways in which this response was more sensitive. Okay, so I actually just made it on time. I had to speed through a bit, so sorry if that was too fast. Feel free to ask questions. So yeah, in conclusion, active inference generalizes and recovers classical social force models. Ad hoc weight parameters can now be reinterpreted as precision weighted prediction errors. Is that just a trivial translation exercise, or is that useful? I would argue it's useful because we get these new ways to like adapt plasticity and adapt beliefs about statistics online. Yeah, and behavioral plasticity, which is we operationalize now as inference about model parameters themselves, kind of introduces a new class of collective motion models where the behavioral rules themselves are changing online, and we get groups that are able to better amplify and encode information, which is actually something that's more biologically realistic, because these old cousin models have this kind of averaging phenomenon that you don't really see in the data, right? Like schools of fish, for instance, are able to very transiently amplify relevant information. The cousin model doesn't do that so well. And this is all in a paper that was published earlier this year called Collective Behavior from Surprise Minimization. And yeah, I know I'm a bit late, but with that, I'd like to thank the team who's behind this. So my PhD advisor, Ian, and co-supervisor, Carl, and then all of these people, Lance, Bear, and Richard, who are instrumental in getting this work together. So thank you to them, seriously. It was a real pleasure to work with them. And yeah, feel free to ask me about my day job where I'm doing machine learning at Verses. That's very different, and it's like kind of Bayesian deep learning. Please come up and ask. If you don't want to talk about collective motion stuff, feel free to ask about that as well. But I'm also very happy to talk about complex systems, collective motion. Thank you all for listening. Appreciate it.